to an actual training course. We're hoping and praying that COVID leaves us. We had to cancel our training course this past summer, but we're going to have a live 4-day course. If you happen to be near or happen to want to visit Lafayette, Louisiana, we're going to have hands-on cementing training, some a unique venue. We're going to go to labs to see equipment. We're going to learn about cutting-edge, state-of-the-art cementing that will include a lot of good food and even an awards banquet the last night at the racetrack. So stay in communication with us about that. You can contact us at these 2 email addresses or through our website, and contact me at any time if you want to talk cementing or have any questions. Let's talk cementing. We're going to have fun tonight, and we're going to be a bit relaxed, but I want to remind us that this is a serious topic. Things like this can happen when it comes to the wonderful but crazy world of cementing. It is an exciting discipline. I hope to show you that tonight as I introduce you to the basics, but also to some advanced concepts. This is the building. I think it's the library, I believe, in Hutchinson, Kansas. This comes from wells that were drilled in a gas storage area. It appears that the gas leaked through the cement. These were cemented a long time ago, found their way into the geologic structure along fault lines, and finally came up under the town of Hutchinson, Kansas, where at least a couple buildings exploded and caught fire. It's serious business. This is, anybody recognize this picture? It's of the West Atlas Sea Drills rig. It is offshore in the Timor Sea. It's Montara, off the northwest coast of Australia. I put out a LinkedIn post here this past week, and I made this statement. If you do not know what happened at Montara, this occurred a time after, but the cause was the cement job. And if you understand, and I'm not sure that even those who investigated this really understand what had happened. And we'll talk about that a bit later, but Montara, this well flowed oil. It was one of Australia's worst oil spills for about 70-something days into the Timor Sea. Right as they were killing the well, it exploded and caught fire. Fortunately, no one was hurt or killed in this accident. We know this one. This occurred in the Gulf of Mexico. Might go down for sure in the U.S. as the worst disaster in the oil field. This is Macondo, happened in April of 2010. Again, the root cause was failure to isolate with the cement after the cement job. Does anyone recognize this fire? And what I'm showing you are 4 of hundreds of incidents that have occurred because of or after or during a cement job. Exactly, Christopher. This is this year. It's Assam. I think they just extinguished the fire just a week or 2 ago. So as we talk about cementing, we're going to be talking about some engineering terms and basics and this or that, but we're trying to seal these well bores, and it's serious, serious business. Someone asked me what my most, this morning they asked me what my most memorable event was in cementing. And it's when I was awakened one night at 10 o'clock. I was on the rig waiting, a deep water rig, waiting for the next morning to do the surface casing. I was woke up and said, the well is blowing out underneath us. We need to cement and plug this well. So I got up, got my coffee, and we did a quick design, and we pumped for the next 6-8 hours to plug off a well that was flowing. There's nothing more serious than to have gas bubbles coming up underneath the floating rig. It's serious business. The agenda today, we're going to look at the basics, types of cement jobs, and we'll look at the basics of cementing, why we do it, cement job design. We'll look at the equipment we use. We'll talk about best practices. What best practices do you use or should you use? We'll then go around the globe a bit and talk about some unique cementing issues from all around the world. I have been now to a little more than 40 countries involved with cementing. I've lived in 6. I've looked at the engineering design or have worked on wells from a cementing perspective in more than 100 countries. To introduce myself again, my name is Kirk. I am with Thoroughbond. It's a company that we run, an engineering firm that we run here out of Lafayette, Louisiana. We do cementing consulting, and we do a lot of bond log analysis. Have some logs coming in later tonight from Europe that will be spending the night interpreting those logs. Prior to my time at Thoroughbond, I was the global cementing advisor for Repsol. Prior to that with Talisman. Before that, I was the global advisor for cementing for Oxy. I started my career with Halliburton, worked there for 23 years, worked as a cementer, a field engineer, went to research and worked in research in Duncan, Oklahoma for a while before I went out and advised at various locations around the world. So I've had the opportunity to see a lot of cementing around the globe and the way we do it differently and the way we do it the same. And so we'll talk about that as we close this evening. The basics of the cementing operation: we take a high pressure cementing unit and we're going to pump cement down the casing into the annular space. And we want to place that cement in that annular space between casing and the hole to seal off the formations. So we'll circulate with our drilling fluid. We'll then pump a spacer, drop a bottom plug, pump cement, drop a top plug so our cement is separated by plugs. We'll displace that down the well, down the casing with mud or water. When we get to the bottom, it will bump. The plug will land on a collar. And all of the cement should be on the outside and drilling fluid or water on the inside. We then wait. Sometimes we don't wait long enough, but we wait for the cement to set up properly. Then we will analyze the results with a CBL or with a shoe test. We will be talking about primary cementing, but we have 2 other areas that we could spend a lot of time on. Squeeze cementing or remedial cementing, where we're fixing holes in the casing, or we're fixing the cement job, or we're actually fixing formations. And plug cementing, where we're setting plugs of cement in the well for a variety of reasons, maybe to kick off, to drill a new hole section, or to abandon a well. We're going to focus on primary cementing for our discussions to the introduction of cementing this evening. And I think we are back. So let's talk about the casing strings themselves. And again, we're looking at the basics here. The first string that we set is the conductor. Offshore, sometimes that conductor is just driven into the sea floor. It's pounded into the sea floor. Sometimes we drill a hole and cement that conductor. On land, sometimes we use a rat hole drilling company and we just dig a hole and then we drop some casing in there, maybe put a bulldozer on top of the casing to hold it in the ground. The first job I ever caught was a conductor pipe, and I thought, wow, this cementing stuff is pretty primitive. But it's the first short string. It may be anywhere from 80 feet to a couple hundred feet of conductor. We center the rig over that first string, and that begins our well. Our next string is the surface casing. We've drilled deeper. We usually associate the surface casing with isolating or covering the freshwater zones. Although in deeper wells, they can be covered by another string. Our next string might be the production casing as we telescope the casing strings into the ground. And here we'll be covering the oil zone or the gas zone. If we have not yet reached our target so easily, this might be an intermediate string, and we will drill out and drill deeper. We might set, instead of a production casing, we might set a production liner, or if we're drilling deeper, a drilling liner. And now we're running on drill pipe a shorter piece of casing, and we will cement through the drill pipe and casing and then hang the liner off on the previous casing. Sometimes we'll connect that back to surface, and that is called a tieback string. And we will cement that string in place on various occasions. Why do we cement? Why do we do that? There are 4 reasons I will list. There may be a couple more, but we umbrella these under about 3 or 4 reasons. Why do we cement? And I ask questions because I want you to talk with me. Plus, it gives me a chance to enjoy my coffee. Why do we cement? What are the reasons? Thank you, Sebastian. Appreciate that. Well security or well integrity. Thank you, Adele. Or Addo. Not sure how to pronounce that. To isolate. For zonal isolation as a barrier. Thank you. Thank you, Perwanto. Appreciate that. That's right, Sheila. To provide zonal isolation in the wellbore. That is number 1, to seal formations that have been drilled. Can isolate production water zones, weak zones, stimulation treatments. Okay, thanks, Derek. To satisfy the government regulations. And they make the regulations trying to achieve, in part, this zonal isolation. Prevent fluid contact to the casing. Thank you. To protect the casing from hull collapse or from casing collapse. Thank you, Mohammed. That's another reason we do, to protect the casing and to support it from burst collapse, from drilling. If we drill out a shoe and we're drilling out the cement, we've had before without good cement there, we can knock a collar off or knock a shoe off, which can cause problems for drilling. Somebody mentioned, Raphael, you did, well control. To maintain control of the well. And again, we're cementing as we go down to protect ourselves from weak zones and from high pressure zones. It's a form of zonal isolation. And then finally, and you've mentioned this, satisfying governmental regulations. I don't know what you were doing last night in Australia or the Philippines, but were you thinking about your cementing philosophy? I don't know how many of you have thought about your philosophy of cementing. By philosophy, I mean a big general idea of how do you get a good cement job? How do you achieve those objectives of protecting the casing, getting zonal isolation? When we cement, we want the cement to come up to the right spot and to seal all the way around the casing. We want it to go into the right place, and we want it to provide zonal isolation. Some big general ideas. Cementing a well bore or cementing a well is like, or here's what you do to get the good job. Okay. Fahid, you want to go to CBLs. We're not going there yet. Is that your philosophy? I like CBLs. To get a good CBL. What is your philosophy for cementing? Sheila, do you have a philosophy for cementing yet? If you're watching this by video, this is the part of the video where you just get to think. Thank you, Dale. To get a good cement and cement job placement. Want to protect the well. Appreciate that. The economic and efficient. I like that. Calculate the appropriate volume and the required time. Volume and time. Pump enough of the cement and make sure it has enough time to get there. Philippe says good formation understanding, proper cement strength without overpricing the operation. Okay. Anybody's philosophies. You have this hanging on your wall at your home or work. My philosophy of cementing is. Thanks, Christopher. Confirming top of cement. Meet your well objectives. Good design of a cement job. Make sure you design it well. I'm going to tell you what my philosophy is, but I appreciate the comments. Very good. Well, I like that too, Philippe. Do it right the first time. It's very hard to fix a well. Here's a couple horses that we have. This was actually our farm in Houston. And so I'm going to see how good of an eye you've got. I've got two horses here. We've got one on the right, lighter in color, and the one on the left who's darker in color. One of these horses is a champion thoroughbred. He won about $1 million. The other horse is the slowest horse on the planet. He was so slow he couldn't race. Which horse, the dark horse or the light horse, is the $1 million champion? This horse was so good, after he won the championship in California, they shipped him to Hong Kong to run in a $12 million race. Now, some of you have a very good eye for horses. The dark horse, the one on the left. Sergey says we can't do an analysis without a CBL on these horses. Amanula maybe has the best eye. The horse on the right, his name is Will-O-Wisp. He was the champion in 2005. He's now a little fat because he's worked hard. Now he's eating. He won about $1 million. On the left, that's Bandit. He's pretty, but boy, he is slow. So it isn't always as it seems, but that's not why I put this slide up. That's not my philosophy. I just like talking about horses. Look at the fence. Do you like the fence? And what do you like about it? The purpose of the fence is twofold. It's to keep the horses from running away. And these are fast, strong horses. It also, we'd like for it to look good. Do you like the fence? It's white, it's clean, but they're straight and they seem sturdy, but it was put together. So I'm going to ask you, if you were going to build a fence, a really good fence, what's the first thing you would do? Now think, don't hurry into this. We're going to plan this cement job, so be very careful here. What is the first thing you're going to do if you're going to have this fence to protect these horses? Okay, start with a good post. Dig properly. Philippe is going to start digging. Let's not dig too soon, Philippe. Put the shovel away for just a little bit. Boy, Gabil is really going to make me work. Is it Gabil? My glasses. No, Sahil. Sahil is going to make me evaluate the strength of that fence. I'm not sure I'm ready to do that. Okay, we're going to design the area where we're going to put the fence, but now we've done that. What's the first thing you're going to do? Sheila's going to go to the store to get the materials. I'm not. What's the first thing we're going to do? It's what I want you to do when you're designing a cement job or when you are working with a cement job. What do you need to do? Let's apply it to the fence. Think with me. What are you going to do? Okay. See, if we weren't running this on video, for those of you watching on video, then we could talk about this all day, but we will move on. What are you going to do if you're going to cement a well? You're with an oil company, or even if you're with a service company, what are you going to do if you're with an oil company? It's what you're going to do with the fence. You're not going to do it yourself, are you? You're going to find someone who knows how to do this. I did not build this fence myself. I thought about it. As a matter of fact, when we moved to our new farm, I started myself. I got about 3 posts in the ground, and I realized that wasn't for me. I was not a professional. I was not good at it. So the first thing I want you to remember, it's so important. My philosophy is cementing a well is like cementing a fence post. And the first thing I'm going to do, I'm going to choose the right fence post cementing company. I've had various people do fences, including myself, and some people do it very poorly. Some people do it very well. You really need to have the right team working for you, and we're going to see how important that is as we move forward. But choose the right fence post company. Then we can start looking at how they're digging the hole and how they're cleaning the hole. We do need temperature, Carlos, and pressure. We'll get there. That's it. Too much detail for me right now. We're going to look at our philosophy. We're going to clean the hole. We want to put that fence post in, and we want to have good clearance to where we can put cement or concrete around that pole to hold it sturdy. We're going to fill it with cement. We're going to set the cement up slow or fast. Well, we debate that in the oil field. We don't debate that when we build a fence post. We're setting it up fast. We will not disturb the cement while it is setting up. I watch them. After they put the concrete in, they don't start wiggling the post. They've got it straight. They've got it perfect. They do not touch it. We will accurately evaluate the results. If we put the fence up and we walk out the next day and the fence is leaning, when we do it over again, and we will do it over again, we'll do it differently. We're going to evaluate the results, and then we're going to improve by observing those results. I don't know why the fence post is crooked. Maybe the cement didn't set up. Maybe a cow, a baka from next door came over and bumped it. But I'm going to evaluate the results, and we're going to improve. And then when we leave, hopefully it will have been safe, and we leave the location clean. Just to repeat, I don't know why I put Laurel and Hardy here. I'm not making fun of service companies, but what I am saying is choose the best one. Choose the best team. Get the best team you can get. You're going to have some engineers who know the issues, know the problems, know the solutions. You're going to have some who will just bring breakfast to the office and not have those answers. We're going to clean the hole. We're going to liken that to the way we clean dishes in the sink. We kind of do it the same way in the oil field. We're going to fill the hole with cement. A fence post hole is easier to fill, trust me, than the oil field hole. And in our oil wells, we have to pay a lot of attention to being able to get the cement where we want it. We want to set the cement up fast. We're going to have a little debate later about how to stop flow into the well. Can we do it with gel strength? We talk about gel strength and critical static gel strength a lot. Or do we need to set it up fast? I argue for setting the cement up fast and do not disturb it while it is setting up. We talked about the catastrophic flows. Almost half of those catastrophic flows in the Gulf of Mexico occurred after cementing, and they occurred as we disturbed the cement while it was setting up. Accurately evaluate the cement job. Sometimes the bond logs are more difficult to read than the map around Kosovo of the roads. I would be lost in this country. Improve. We monitor results wherever we worked, whether it was at Oxy or Repsol or Talisman. We need to get above 95% success. Because you have one success, that may not be that you're using the right answer. That has to work almost every time. We'll talk about that when it comes to float equipment, for example, here in a bit. If it's not working at least 95% of the time, you need to be working hard on a better solution. And then safe and clean. I think this is still the world's tallest building in Dubai. They say, I haven't seen this, but they say that the men cleaning the windows do it year-round, up and down. It is clean. I don't know about safe. Let's talk about job design. What we're going to be looking at with job design, as someone has mentioned, we want to make sure we have the right volumes of cement that we're pumping. We want to make sure we have the right density and we're pumping at the right rate. Both of these will cause pressures in the wellbore. We want to have the right slurry design. Besides density, the other important properties. We'll be spending an entire webinar on designing the slurry and another one on testing the slurry. So here in the future. In the job design, we need to know operational aspects, how we're going to do this on location. What do we do when the job is finished? And then evaluating the cement job. We're going to focus on the top 4. In our later webinars, we'll look at the post-job activities, and we'll definitely have a couple webinars on cement evaluation. When it comes to cement volumes, I have this. I actually have 3 copies here that sit around my desk. I constantly am looking at the red book. I don't know why I don't just memorize everything. I have some memorized, but I use the red book. Many of you may have a blue book or red book on your computer electronically. I don't know. At a certain age, you can only read things on paper. It's a crazy deal. But we're looking for volumes, and we get the capacity and we get the factors for those volumes in this book. We're looking at the open hole volume. We're looking at the casing by casing volume as we lift cement up into the previous casing. We're going to have a volume of cement that's in the shoe track. And we'll have a volume. It's the Bible, right, Dale? And we will have a displacement volume. Those of you watching on video, sometimes I'll shout random things, and that's because I'm receiving a text message. So out of nowhere, I just say, it's the Bible, right, Dale? Well, he said he has his red book with him. And that displacement volume will calculate from the capacity of the casing. As we do that, part of our volume may be tail. The tail cement is a stronger cement. We usually want 500 psi of compressive strength before we drill out and move forward with our operations. In part will be lead cement. The lead cement is a weaker cement, sometimes too weak. I think Railroad Commission standards allow us to only have 250 psi in 24 hours, which means often the cement is not set when we're disturbing the casing, nippling down BOPs. It's a lower density usually, and we need that lead cement so we don't break the formation down. But we run the types we do because we get a high yield and it's economical. We save money. When it comes to volumes, we have excesses. We can caliper the hole, a mechanical caliper that we can run, or we might run a fluid caliper to measure how much of the hole is circulating. And we'll add 15% to that volume. Or a surface hole, we may run from 100 to 200% extra cement to fill the hole. And the production casing maybe from 20 to 50%. And we learn by experience. And thank you, Christopher. That excess is not applied to casing by casing. Thank you for the comment. We will confirm these things by watching the volumes on location. So we have a surface hole. I remember one of the first surface holes for this particular company, we got back 200 barrels of cement. And the drilling manager was not happy. He said, I want 1 barrel of cement. I don't want to waste 250 barrels. So we cut back and then we didn't get any back. And then you add a little more excess and you get too much back. And when you start measuring your volumes, I would recommend that you can use an indicator as shown on the right. Phenolphthalein we can put in to indicate this base of cement and it will turn red. But measure the density because we can get indications of cement and it's just a trace of cement. It's not good cement back to surface. So we will confirm our volumes either by finding the top of cement on bond logs or temperature logs, or by measuring our volumes of good cement back to surface. When it comes to the density of cement, the density and the rate, we're working along these two curves. To the left is our pore pressure. To the right is our frac gradient of our hole. To the left is the pore pressure of our formations. When we cement the well, both while we are pumping and when we are static, we want to fall in between these two curves. We call it the ECD, or the equivalent circulating density. We're relating that directly to an equivalent mud weight. If it's too high because we're pumping too fast or because the density is too much, and we cross that, we're going to have lost circulation. And if we are too low, we will have either static, usually will occur when we're static, or while we're pumping, then we're going to have an influx and a flow. So we want to stay in the middle. Here's the design and the output. Here's our pore pressure down here. Here's our fracture gradient up here. The top curve is while pumping. The bottom curve is while static. And in both cases, we fall between the pore pressure and frac gradient. The same is shown here as we go up and down the well. The previous slide was at a certain depth. This is up and down the well, our pore pressure, our frac gradient. A minimum line is drawn for our minimum hydrostatic, which is a ½ pound over our bottom, our highest pore pressure. But again, while we cement, we fall in between the curves. And so we wanted to design a density and a rate that achieves that. But of course, when we design our density, it's part of our design that will involve our strength, our fluid loss, or viscosity, a lot of things. We even take it further with simulations, and we simulate displacement efficiency. The dark colors here are the cement. Looks like it's going up here, it's going up the wide side of the well. Here, we're moving the casing and we're simulating a better interface. Here we're showing channeling. I would just warn you, this is helpful, but confirm these things in the field. This is theoretical. There are a lot of assumptions made. Very helpful, the simulations are, for displacement efficiency. But remember, they are simulations. Besides density, we have other slurry properties. What other slurry properties? We mix them up in the lab, and we have to pump them in the field. We mix them in the lab, and we'll talk about that in one of our future webinars, but we do it in a Waring blender. It's like mixing up a milkshake or a strong drink, and we mix it up and test it, and then we take it to the field. What properties do we test or do we focus on with cementing? There are 5 that we test every day. Do you know what those are? Dale is quick with the draw. We've got viscosity and fluid loss. Those are 2. Raphael, I think with a homogeneous mixture, you're talking about no settling or segregation. We've got thickening time. Thank you. Christopher, we do have the density. This Vahid says the setup time, or also the compressive strength. Okay, I think we got them all. We test 5 every day. One of the most neurotic positions, is there such thing as a neurotic position? Neurotic positions in the oil field is a lab technician. He does these 5 tests. I know, I've been a lab technician many times. We do 5 tests all day long, every day, every week of every year. We do test after test. And these are the 5 tests we do. The number one critical thing that we look at is temperature. It affects these properties more than anything, and affects our design. Pressure does as well, but temperature, bottom hole static, and bottom hole circulating that we can calculate, or we can use charts. We have formulas, or we have simulators to calculate bottom hole circulating temperatures. We have thickening time. These are the 5 every day. So if you test these correctly, that's good. But if you test these wrong, you do them every day, it's hard to break that habit. We'll look at that when we talk about cement lab testing. Thickening time, fluid loss, viscosity. When we talk about viscosity, we're talking about things like yield point, plastic viscosity or yield point, the mixability of a slurry, and the gel strengths. We can measure those in our rheological testing. Free water or settling or a homogeneous cement slurry. Fluid loss is when you press the water out of the cement with pressure. Free water is when the water floats out of the cement. It's also related to settling or the settling of solids. We see that. And we have many other tests, but these are the 5 basic tests we use. And then finally, compressive strength. When does it get hard so that you can tap on the cement? When we test, and here's a thickening time test, we are stirring the slurry at bottom hole temperature and pressure. And we're measuring its consistency, which is like viscosity, measured in Bearden units. But what is thickening time? If you could put a sentence on what is thickening time, what would you say? I kind of draw a picture of it here, but if you had to put thickening time in a few words, what would you say is thickening time? What is thickening time? Leo says setup, and it's getting close. It's not necessarily when the cement sets up. It's not necessarily the setting time, because at the end of the thickening time, Dale will say when it becomes close to unpumpable. Thank you. It's the time that it's still liquid or pumpable. At what time does it get too thick to pump? At that point, it still may not set up for a long time. But even on thickening time, we can get some different values. Here we have temperature and we have the viscosity on the right. I say viscosity, it's consistency in Bearden units. And look at these three different thickening times. Here we have where we get off the straight line and we see our first gelation, our point of departure. Has anyone heard of POD, or point of departure? Have you heard that term before? Okay, Dale. See, Dale, you're an old timer like me. We never used that term. The point of departure, I'm not sure who came up with it. Was it Halliburton or Schlumberger or someone else who came up with point of departure? Anyway, sometimes you're going to hear terms or factors or numbers that you haven't heard before, and you'll think, wow, I don't know much. Well, you might know a whole lot more than even those who came up with the term. Sometimes new terms come on. Usually service companies will throw them in and see if they catch on. But some will use point of departure as the thickening time. As we gain a little viscosity, let's call that the thickening time. Others will use, especially for lightweight cements, when it reaches a measurement of 40 Bearden units. Most of the world, not all of the world, but most of the world uses 70 Bearden units. API, for purposes of testing neat cement, they use 100 Bearden units. I guess one lesson about point of departure is don't worry when you hear new terms, just figure out what they are. They may not mean that much. Some of the things we did in research, afterwards we said, well, we were wrong there, but it already got out and people are talking about it and using it, and we couldn't keep the genie in the bottle. When we talk about job design, we've talked about volumes, density and rates, slurry design. Let's talk about cementing operations just a bit. Then in other webinars, we'll talk about post-job activities and the cement evaluation. Talking about operations, let me introduce you to the equipment that we use in cementing. I throw it into these categories. We have the bulk cement, the mixer, the pumper, monitoring equipment, and then we have the tankage that we use. And we have a few other things that we talked about, like centralizers or float equipment, and we'll look at those. This is the general setup for our bulk cement. We're going to mix cement. We can use liquid additives for sure, and we'll use those usually offshore, but onshore as well. But assume we're using all dry additives. We blend it and mix it all up at the bulk plant. We have our cement storage. We're going to weigh our cement into the scale tank. And then when we do that, we can take it from the scale tank and put it over into the blend tank. We will then cut our additives into the cutting bottle. Whatever additives we're using, we'll take half of those and put them on top of the cement. We'll weigh more cement, put it on top of that, and we will layer cement, additives, cement, additives. And then we will blend those by moving them pneumatically. Dry cement with dry additives, 1, 2, 3, and then to the truck or to the barge if we're going offshore. Every time we move it, we call it a boxing, and we're blending the cement to get a good mix. So we're going to do that here. The additives at this location, this happens to be actually in Los Angeles, California, almost downtown Los Angeles, they have a cementing plant. I think it's still there. The additives are inside, and the scale tank is. It's layered into the blend tanks, and then we go 1, blow it back over here 2, blow it back over 3, and then send it to the truck. We sample it, and we keep a sample of the bulk plant cement, and we send it to the truck. The truck goes to location. Here's the truck on location. We're going to take that cement, sample it again on location, but we're going to send the cement through the hose. We're going to blow it in there at about 30 psi, and that is going to blow right straight to the cementing unit right here, and the cement will go in. Do you see this cementing unit here? Do you know whose cementing unit that is? Can you tell? It's not blue. And Andres, it's not, it is red, Corey, but it's not Halliburton. I just want that to be clear. This is not a Halliburton unit that I'm showing. Okay. Now that that's clear, we're on video, that's not Halliburton. The dry cement goes in here. The dry cement will go down. There's a water jet coming in, and there's a jet here where we will wet the cement. It will drop into the tub. We'll stir it up in the tub, and we'll recirculate it back through. So we have a recirculation going on, similar to the Halliburton unit and to other units. But the dry cement goes in, it is mixed, goes into the tub, and then is recirculated back into the mix. It is a recirculating unit. It goes into the tub. The tub is being stirred with paddles. The first time I ever cemented a well, I was 22 years old, and I went out to cement a well. I forgot to turn on the agitators. And the cement, it was a squeeze job, but the cement was just all dust. And by the time I could see cement, it was all dry powdered cement across the entire tub. I didn't know what was going on. So I started hitting it with the water hose, and then I remembered, engage the clutch to turn on the paddles, and I did that. And before long, we broke it all up, and we had a beautiful cement. But my first time on the cementing unit was almost a disaster. So we have a lot of mixing energy going in as we mix the cement, but it also, by recirculating it in the tub, we add mixing energy. Sometimes we have trouble mixing this and going down hole. We have trouble mixing the cement. A lot of things can happen. Not only if you're 22 years old and you're not a good cementer, but we can pack off the cement. We can have poor delivery. We can have some issues. It can be too thick. We are going to measure to make sure we're having the density confirmed at this point. And we can pump it down hole, or we can batch mix it, pump it into a tankage, into a batch mixer, and make it a consistent, beautiful cement going down hole. I'm working for someone right now who does not like to continuous mix. He likes to batch mix, and for good reasons. The last job I went out on, it was hard to mix the cement, especially on some land units. So sometimes we will batch mix. Sometimes it's so big, the jobs are, we have to continuous mix. So we will take, whether from a batch mixer or from the tub itself, and here's the tub on this particular unit, that will be sent to either gravity fed or boosted to the suction manifold, which will then enter the high pressure pump and be discharged to the rig floor and through a cementing head. We had already run the casing at this point, and when we ran the casing, we would put the centralizers on, a very important piece of equipment. Here we're shown putting the centralizers over a collar. This was on a job not too long ago I was out on. And then the cement, though, as we start to pump it from the unit, the casing's already been placed. We're going to pump the cement through a cementing head In that cementing head, we have, in this case, a double plug container. So we have a bottom plug, which has a disc that will burst so we can pump cement through it. And we'll have a solid top plug. You can't pump through this one. When it lands at the bottom of this well, the job is over. So we'll put those in the cement head, and we will circulate the well. We're circulating the well with drilling mud. We'll also pump our spacer at this point. We'll then pump through a different valve. We'll pull a plunger out and allow that bottom plug to fall, and we'll pump cement on top of that bottom plug. And we'll pump all of our cement on top of the plug. We will then displace, as we pull the plunger and allow the top plug to fall, we'll displace the well and send the top plug down. When the top plug lands, we should have all the cement on the outside, and we should have our displacement fluid on the. When we bump the plug, here's what we end up with. Our bottom plug is hit. Now this top plug is going to land on top of it. And when that occurs, it lands on a float collar. We should have our shoe track filled with cement and cement up our annulus all the way. If the float collar fails, in other words, this float, all this cement we lifted wants to come back in because we have a pressure differential. This float is a check valve that blocks that. If it fails, what do we do? What do we do if the float fails? Cement's trying to rush into the wellbore. Thank you, Ponville. We hold pressure. We do that by shutting in at the rig floor. And we trap pressure. Now, here's something that we never used to do, and everybody does it now. And I don't know if we've talked about, I've never talked about this actually. If the floats fail, we get a volume of cement coming in. Everyone wants to pump that back down. I'm not a big fan of that, never was, but everyone does it. So maybe it's okay, I don't know. I just usually like, okay, it failed, let's shut it in at that point. Atif asks a good question. What about if it's a liner? Good question. If the floats fail on a liner, and I've got a set, I've promised some people a set of liner best practices. But the general best practice in there is we shut the well in for 15 minutes, or we wait 15 minutes, and then we proceed. We want to set the liner top packer and then get out of the well. We don't want to hang out down there holding pressure on the well in a liner situation. And if we get the liner top packer set, that's going to help us out quite a bit. Good question. Let me ask you another question. We're going to get back to Montara. One reason, if we don't bump the plug, I'll show you this very quickly. This was a liner dart. I'm talking about a liner. We didn't bump the plug. And when we pulled the drill pipe out of the hole, this is what we found in the drill pipe. Our launching dart that was to launch our plug had gotten torn up on the way down. And that's why we never launched the plug, and that's why we never bumped the plug. But when we bump the plug, if we do, and the floats do not hold, we talked about that. What do we do if it's in this position? What if we're in a horizontal well and the floats fail? What do we do? I bring this up because this is one of the aspects of what happened at Montara. The floats failed, and Montara was a horizontal well. It was a sidetrack that went horizontal, and it was finished in the production zone. And I don't remember if it was above the water leg, I have to look, or if it's down into the water leg, but it was a horizontal well. What happens if the floats fail in a horizontal well? What do you do? The cement's going to try to flow back in. So what do you do? We drilled a few hundred horizontal wells in a certain area. And the first 200 wells, our floats, listen to this, our floats failed 25% of the time. And something interesting happened when those floats failed. You will find that floats will fail when you have horizontal wells, when you circulate a long time, especially getting that casing to bottom circulating, and when you're at a hot temperature. There is a line, I don't know where that line is. It may be 240F, it may be 200F. These wells were from 270 to 300F, and the floats would fail, wherein all of our other wells in lower temperatures would not fail. So what you're going to do, you're going to shut in the well just as you normally would to stop the cement from flowing in. But it's not going to help completely, is it? Because now here you have cement in the shoe track. Here you have water or mud. And although you're trapped in, they're going to try to swap. And you're going to get clear fluid on top or mud on top. You're going to get cement on bottom. I would say every, there may be an exception, but every failed float in the horizontal that we had, we also failed the pressure test. We had a wet shoe. We pumped through. Montera doesn't mention this in their report. I don't believe in their final reports. They talk as if the shoe was over displaced by cement, but if they had failed float, and they did in the horizontal, what you need to know, even if you can't fix it, you need to know you have a wet shoe and you're exposed. When they went back into Montera and they removed the corrosion caps, they opened themselves up to the well, it blew out. They knew they had failed floats. They didn't necessarily know they had a wet shoe, but a failed float in a horizontal well is a wet shoe. There's a question about that. That's not brought up in their report. Matter of fact, they talked to the cementing experts afterwards, and most said, we don't have experience with failed floats in a horizontal well. Yeah, I said a wet shoe, and I'm sorry, that's a terminology for that shoe track. And we can back it up. This shoe track, if you can pump through it, it should be filled with good hard cement. But if you can pump through it, or if you drill it up and there's nothing there, then we call that a wet shoe. It's a shoe track that doesn't isolate. Montera occurred 9 months before Macondo. One of the main causes likely of Macondo was the fact that the shoe, the cement in the shoe track had disappeared, maybe was unset, was contaminated. Regardless, that's likely that the flow came up through the shoe track in that case as well. Well, let's move on. We're going to have to get going. Let's talk about best practices that you use. What best practices do you use? I'll show you a couple here. One I have here next to me, I better know this. I don't know if I know it well enough, but every well in the Gulf of Mexico, post-Macondo, you better adhere to the RP 65 or the API standard 65. What we do and what I recommend, it's really good stuff in here, but take what's in here and make it more specific. Apply it to your local well or your local field. As we go around the world and look at some of these wells, we will in a bit here, you need to know what works in your area. So you take the general, and there's a lot of general stuff in here, like thin the mud. You take the general, and you should have a document for every operation you have. The document that we're using here for this particular oil company is a 14-page document of exactly how we run casing and cement these wells. We take some theoretical. We're going to talk about some of the theory that's in here, and we operate not on theory, although we'll use it, but on what we see in practice occurs. And I'll show you an example of that. So take the general and the theoretical and apply it specifically to the practice of your field. I'm going to touch on just a few basics or general, and let's look at cleaning the hole. Just like there are 5 tests that we do on the cement, for every job, there are 5 things that we do to clean the hole on every job, or that we can do in the industry. The first is to centralize the pipe. The second is to condition the mud. I like to compare these to the way you clean the dishes in the sink. I don't know how many of you do that. I think I used to do it a lot, but then I got really busy. So my wife says I don't do it that much. I say this, I do clean the dishes, but before I can do it, she usually does it before me. So it's kind of one of those deals. Think about cleaning the dishes. I look at it as the way we should clean the hole. When we centralize the pipe, we do so that we get flow all around the pipe. When we clean the dishes, we move the plate around so that we touch all corners of the plate. When we condition the mud, we get the mud in a condition where it will go out of the hole, where cement can replace it. In the kitchen, this is one of my problems. If you take the food on your plate and you don't touch it for 1 day or 2 days, you can't remove that food from the plate. It's very difficult. So when we condition the mud, we pump a thin mud ahead to get it moving. We circulate whole volumes, 1.5 or 2 whole volumes. We don't let it sit around. And we can even measure the circulatable hole, look at our standpipe pressures and some other things to condition the mud properly. We use effective spacers. What spacer do you use when you clean a dish? You might put soap in it, but you use a water. You use a turbulent spacer. And Atif, I'm answering your question here. I've worked in-house at several operators and often will pump up to 200 barrels of a thin mud before the spacer. We found that to be beneficial, yes. From the spacer, we can argue thick versus turbulent, reactive, whether you put soap in it for oil-based environments. In the kitchen, we use water. When we open that faucet up, we want a thin fluid to come out to clean our plate in turbulence. I'll just say that much. We don't want thick fluids coming out of the sink to clean our plates. We will turn the faucet on full speed or a high flow rate. We want that in the oil field as well. And we want to scrub it. We want to scrub the plate. A very effective way to cement is to rotate or reciprocate the casing while we pump the cement. Well, let's take some time and let's go around the world and do some more cementing if we can. We're going to go for about another 20 minutes. At the end of that time, we'll have a time for questions and answers and discussion as well. Let's cement the world a bit. We're going to look at wells that are cavernous, full of gas, hot, cold. I used to call wells ugly. I'll ask you what an ugly well is here in a bit. Corrosive and crooked or deviated. Let's go to cavernous wells. Here we're flying on our way to a cavernous well. Do you take a guess where this might be? We got mountains, we got some snow. See if this helps. Here we're going up the road. Do you know where this is? Here's another picture. At this point, I took a picture. I'm scared of heights. There were trucks flying down this road, and I said, can we please turn around? No, I said it more emphatically. I said, turn this truck around. It took us about 5 minutes to get the truck to turn around, and down the hill we went. This was a muddy road. We had no chains on our tires. It was pretty scary. Do you know where this is? Take a guess. We're getting close, Derek. No, not Brazil. Pretty close to New Mexico. This is near the Rockies. It's in western Colorado, up on the mesas of western Colorado. And if we go back to this picture, one of the problems is we're drilling from here down through the mesa. We drill wells in the valley, but we drill wells up on top of the mesa in the Piceance Basin. And you can imagine as you drill this well, our pressures, our frac gradient, sometimes we're connected to the mountain. Our frac gradient is at atmospheric. And you have a crack and you have atmospheric pressure. It's very hard to lift cement above that. These cavernous wells, the losses are quite severe. Maybe worse than that is the UER in the Middle East is a formation that is tremendously difficult in certain places to cement across. I put a post on LinkedIn recently and I asked, what is the worst situation you can have? And I meant it to be like, what's the most difficult problem worldwide with cementing? I got back a lot of unique answers like hot, cold, corrosive. I got some of these answers back and it was really neat to see some of your most challenging wells. But here's my answer, and that is lost circulation. Weak formations, the most difficult thing all around the world. We have to deal with that. We do so in a number of ways. Here are a few. We need to stop losses before we even run the casing. While we're drilling, we need to fix those losses. The worst point is when you're cementing, you get more pressure, less annular clearance, heavier fluids. So we need to stop the losses. Before we pull out of the hole, we can spot an LCM peel. We do that quite often. We run the casing slow so that we don't surge the well. Speaking of running fluid loss additives, or I'm sorry, loss circulation materials, you have to be careful running in the hole. We want to close our floats or we can plug those. We think that happened at Macondo. We pump those thin muds ahead. Thin cements from an ECD standpoint, but we can pump some thicker reactive crosslink spacers. We've done that successfully. It goes down the cavern slowly. The cement passes by and flash sets it, and we can cement the wellbore. Very effectively, we have used that. Foam cement is a great option where you can run foam. Hollow spheres. Make sure we simulate the ECDs. If you have losses, initially, immediately slow the pumps and hopefully get the returns back. We can also use stage tools. We won't talk about those because of the time frame. Sometimes we think of it, if you can swallow it, it probably doesn't work for severe loss circulation. Sometimes we have to pump solids into the well. I remember jobs in Libya, for example, where we would pump gunk squeezes, or in this case, it's super gunk, or we'll also run a diesel oil cement, and we mix that, an oil base full of bentonite and cement, we'll mix it with water below the bit and it turns into a solid, and we stuff the caverns with the solid. Wells full of gas. I happen to show another picture from the Piceance Basin, which is a gas field. The opening slide of this webinar was a gas well in Kurdistan. Often we think of gas, we're thinking of deeper, higher pressure wells. How do you stop the flow? Very important this is, and we could spend a lot of time on this. We're going to have a separate webinar explaining this specifically. But critical static gel strength, you hear about it a lot. I was just at the University of Louisiana in Lafayette, and that was a main concern what they're testing for. Let's design for critical static gel strength. I want to kind of clear up or talk about this. This concept actually was written about and even is referred to in this API document, a document that was the paper that refers to critical gel strength was written 40 years ago. It's kind of old theory or old testing. But critical static gel strength is taking the overbalanced pressure times 300, dividing that by the length of the cemented column and the clearance. We call it the effective diameter, the clearance, the difference between the hole size and the casing size. And we calculate the critical gel strength. Then we test it in the lab. And we measure the time it takes to get from critical gel strength to 500. And the shorter that is, the better. The problem with this is that gel strength does not stop flow, in my opinion. It stops the percolation of certain size bubbles, but you need set cement to stop flow, not just gel strength. So when we're looking at what stops gas flow, make sure we write it from practice and put it into our local practices. Here's one local practice we have. Very specific. The casing will have the mill varnish removed from the OD to enhance cement bonding. This is a different kind of gas flow. It's gas flow along casing cement. This well flowing gas, it's not a blowout, but an offset from this well did blow out. But here we see where the gas is coming from through this ultrasonic bond log. You'll see little river patterns on the right. You see those? Those are channels, casing to cement bond, where we're percolating gas through those channels. In that case, we're able to shut it off. It may not be percolating gas. It could be full blown out cross flow that's wiping out cement, as shown here in well number 1. Trust me, gel strength will not stop that cross flow. You need compressive strength or a mechanical barrier. This is a 200 psi over a short distance cross flow of CO2. If you start operating in the world of critical static gel strength, you will not solve this problem. We have to think of it in more practical terms of compressive strength or mechanical barriers, or some other thoughts. Compressibility is one to stop gas flow. You might use a compressible cement or a fast setting right angle cement, or to set a liner top or an inflatable packer. Low fluid loss will help stop gas flow and not disturbing that casing. That well that was percolating gas before, we disturbed the casing, and here came the gas. Philippe, no problem at all. Philippe is asking, could you describe the hollow sphere? There are a few different kinds, but they're either a pozzolan sphere, just a little microscopic sphere full of air. It's a hollow sphere. We put it in the cement to lighten the cement. It can be a pozzolan sphere that will crush under pressures, or it can be a hollow glass sphere that's rated for pressure, and it gives you a light cement that's strong. And that's what we use the hollow spheres for. How about wells that are hot? Here we're going to somewhere. Where is this? This is not Brazil either, actually. Where are we at here? Spent a lot of time here. It's close to the UAE. It is not Texas. Now, Dale, I spent a lot of time in Australia. I never saw a camel. Well, one night after a real late night, we had a good time, and then I did see a camel maybe, but this is in the beautiful, wonderful country of Oman. When we have a hot well, here we're looking at a steam injection field where we're heating the wells up to over 500 degrees. When we do that, we will add silica flour. How much silica flour should we add? And we will add it when the temperature of the well usually is above 230 F or 110 C. 35%. Why 35%? I need to read some more work on this. Why would you run 65% silica flour? You would do so in very hot wells if you tested it. Most of the testing that we did in research, we needed more silica flour for long-term strength. For lightweight cements, we may go as low as 15% silica flour. Because for lightweight cements, if you put too much silica flour in, you can't get the cement to set good at low temperatures before steam is applied. Okay, thanks, Dale. Dale saying he used higher concentrations. But generally speaking, 35% is the number. I don't think that's any better than 30% or 40%, but that's kind of the number we landed on. I'm sure there's some work somewhere to confirm that. I want to point this out as far as steam injection or geothermal wells. Here's a big problem. It's in deep water wells this occurs as well. You cement the well and you have losses, and so you do not get cement to surface. For a geothermal or a steam injection well, you want it to surface. What do you do at that point? What do you do if you have losses and the losses are low, or you feel your weak zone is quite low and you have total losses? We get on this well, we start to circulate before we cement, and we have losses. And we pump our cement job with total losses. What do you do, not on the next well, what do you do on this well at that point? We slow down. It doesn't help. We still have total losses. What do you do? What would we normally do? I remember the first time I did this. I'm not saying it was a mistake. I'm just saying I didn't understand what I was doing. But what do you do? And this well is an example of that. Well, we have to cement the well. And we can go out and we can fix it at that point, but we're on the drilling curve now. Or while we're pumping cement, we get losses in the middle of pumping cement. What do we do at that point? Yeah, we could do that. That's a difficult one to, in the middle, start saying, let's go with LCM. As a matter of fact, the cement already has LCM in it. We reduce the rate, it doesn't help. And I'll move on here, but well, what some will do, what we did here, is when you are through, and you could try to fix it with a hesitation. Thank you, Derek. But when we're through with the job, we pump cement down the top. We do a top job to fill with cement. And as we do sometimes, that cement goes away. So we pump another top job and that goes away. And the final top job seems to work. And look what we end up with sometimes. We get top of cement somewhere here, and then we get top of cement hanging on a collar or a centralizer. And we have solid cement to surface. We have solid cement here, and we have a gap. And then we apply steam, and what happens? Casing and casing, we have a trapped area, uncemented, and we collapse the casing. The annular area bursts or collapse the casing. A common issue. Be careful. There is a way to do a top job to try to get rid of the gaps. And we need to be aware of that. So for steam injection wells, we're trying to protect the casing. We want it to last. So we put silica flour. It probably is going to be lightweight, a lot of it. And we also use those hollow spheres and foam as insulators. Note taken, Derek. The only problem is we hate poking holes in those steam injected wells, but point taken. For the steam injection wells, we can run foam cements, hollow spheres, back to those, resilient cements with lower moduli of elasticity, or corrosion resistant cements. Wells that are cold. Where are we flying here? Once again, it's not Brazil, and it is not Oman. It's very much like Alaska. We design cements for this area very much like we do in Alaska. This is actually flying over or landing in a major city, and Philippe has that. It is Moscow. We're flying into Moscow here. Then we're taking back off, and we're flying over this part of Russia in western Siberia. And when we're cementing these wells, I remember this particular, the time I spent in Siberia, we would drive up these roads full of ice going 80, 90 miles an hour on ice. I survived that and realized I was going to live to be about 110 years old. If I was going to die young, it was going to be during my time driving in Siberia. But there we are cementing across. Also in the Arctic, in Alaska, we're cementing across the permafrost. Here we're in western Siberia. When we do that, we use an antifreeze, so to speak. We design antifreeze cements. Instead of water, it's antifreeze kind of water. We keep the heat of hydration low so that we don't melt the permafrost significantly. And we test the cement for freeze-thaw, that thermal cycling, only it's freeze-thaw cycling. When cement sets, it exhibits a heat of hydration. It's an exothermic reaction. Here we show the difference of a very hot cement. If you put it in a vacuum tube, it gets really hot. But here, our Class A cement going up to 150 degrees as it sets, where the cements that we would use for the permafrost are down lower. Corrosive environments. We'll close here in just a couple minutes. Take a guess where this is. I used to recruit engineers for this area. We would actually fly the engineers at night and fly them back at night, take them to the country club while they were visiting this place. It's a rugged beauty, quite rugged. It is indeed Midland, Texas. Thank you, Derek. We're flying over West Texas. In West Texas and up into New Mexico, formations there can be very corrosive, or we can be flooding with CO2, which can be corrosive. Our geothermal wells, our wells close to volcanoes, can be quite corrosive. So we test our cement for carbonic acid, and the cement's dissolved. There's a dissolution of the compounds in cement. So we test a lot with carbonic acid. Here, this work was done in Hobbs, New Mexico. And we see corrosion, the leaching out. These samples were put in the side of a volcano in Sumatra. A sulfuric acid over weeks or months will dissolve the cement. On the right, on the left is a corrosion resistant cement. Hydrochloric acid. We tested some samples of hydrochloric acid on cement that melted the cement because some of the additives in that cement would dissolve. We're not acid resistant. We're very acid soluble. When we cement corrosive wells, we use additives to lower the acid solubility. We also use additives to lower the permeability. If we can't get into the cement, it's hard to dissolve it. So permeability, low permeability is quite effective. Certain additives we'll use will be pozzolans, will be latex. The anti-corrosion resistant cements are calcium aluminate cements. They use calcium phosphates. The things that protect your car from corrosion protects the casing in the cement. And we expand the cement to tighten the bond so we don't get corrosive fluids traveling up through the cement. Wells that are ugly. Do you know where this is? And again, we'll be only 2 more minutes, and we will have a time of questions and comments. Do you know where this is? You would think it's Midland, Texas, but it's a little too many mountains for Midland. A lot of places that have oil look like Midland, Texas. Maybe this will help. Very close to these wells, you'll also find this. As you drive to these wells, you can take a left. You don't have to drive too many kilometers. You can go over and watch the killer whales attack these seals on the beach, if that's your interest. Pretty interesting. I don't know if you've seen this. Pretty crazy. Do you know where this is? Are there killer whales in Australia? I know there are great whites, but does anybody know where this occurs? No, it's not in Canada. In California. Let's go there real quick. It's down in southern Argentina. Again, a beautiful place down there. Thank you, Rafael. I circle Comodoro down south. Again, this is a wonderful place. And you go south, you have oil fields down there. I call them ugly wells in a most beautiful, incredible country. But when we cemented wells down there, we had a lot of washouts. The hole conditions weren't good. Sometimes I call Colombia some ugly wells or other places because the wells are so tight. They don't have washouts. They're so slim, it's hard to get the casing in the ground. But it is tough to cement certain wells. And so we need to stop the washouts, use the right drilling muds. If you have washouts, you can slow down and use buoyancy effects instead of velocity effects to cement the well. And finally, we'll close with cementing crooked wells. Here is a schematic of all of the wells being drilled in this area off of these places. 1, 2, 3, here we're showing 6, 4 major places and a couple small places. Those places we're drilling wells, here's one. We're drilling them off this island. Do you know where this is? One of my favorite places in the world. Where is that? Anybody been here? Great place to visit, great place to cement wells and do work. Ah. Thank you, Mark. I didn't know you were there, Mark. Hello. Correct. It's in California, south of Los Angeles at Long Beach. This is where Thumbs is. Some of my favorite places down here, one of my very, very favorite places to go, Catalina Island. Just a short boat ride from Long Beach. Here is where we have a cementing base, almost in downtown Los Angeles. I showed you a picture of it earlier that did service work for Thumbs. I don't know, this right here I think is Brad Pitt's home, located up here. Cementing crooked wells, it's about centralization. The only thing I'll say, we can talk about centralizers. Here's a little model of my favorite centralizer, which is a Centec It's a rigid bow centralizer, but you can use a lot of different types. We successfully in Midland used the centralizer on the right, a full gauge rigid centralizer to successfully cement. But the type, the size, how those bows go out, or how, if it's full gauge or under gauge, and the spacing. And I think we're a little bit too optimistic sometimes about the spacing. But sometimes I think we need more centralizers in a certain spot and maybe less in others. But centralizers are always that controversial thing. But I see and look at a lot of wells, at a lot of bond logs, and I see way too much of this. With no centralizers on any of the joints of casing, you see the channel. Very obvious. With one joint, which spacing says that's all we need, we still see quite often, see the low side channel or the low side thin cement sheath. And when we get up to 2 per joint, then we start getting the cementing we need. Centralization is critical. Running centralizers, especially as we make the hose smaller, is difficult. One of the biggest challenges that we have is centralizing that pipe and getting cement all the way around the casing. Well, thank you for attending the webinar. I'd like to close by making these following statements. Cementing is critically important to the industry. Sometimes I believe the oil companies try to kind of do it on their own or figure it out on their own. It's not that easy. We've been doing it for 40 years and we still learn something new every day. Sealing the well bore is critically important to the industry, especially during this time of the political things that go on and the release of gas into the environment and environmental issues. We need to seal the well bore. Designing the job requires an understanding not just of a document, but of the actual field you're working in, and to really focus on how to cement that well and the challenges that are unique to that situation. You need to pay attention to the details. It needs to be specific. It needs to apply. As we just saw, cementing operations, very diverse, very difficult challenges, but what an incredible challenge. I've had the opportunity to travel the world, work with some of the most incredible people in some of the most beautiful, even if sometimes ruggedly beautiful places. And the challenges are in the thousands that you could number of the different challenges you find in cementing engineering. So I hope you continue the journey with us as we talk about cementing and this, what I believe is an amazing discipline. Well, thanks for attending the webinar. I'll now have time for some questions and answers, and we can talk cementing more.